Okay, hello everyone. I'm Wang, postdoc at Indiana University. Today, I would like to share with you our recent progress on the stellar obliquity measurements for exoplanets. Here is the inferred true stellar obliquity for hot Jupiter systems based on all the current measurements. X-axis is true obliquity ranging from 0 to 110 degrees. The y-axis is the probability density function. It is obvious, right? Most of hot Jupiter systems are aligned. However, a significant fraction of hot Jupiter are misaligned. Why is that? There are numerous origin mechanisms that can explain such kind of misalignment in hot Jupiter systems, which can be generally divided into two groups. Here is a summary plot brought from Albright review paper. For the left one, first category, the basic idea is the spin-orbit misalignment in hot Jupiter systems is a general process. It is primordial or universal, which can apply all the types of exoplanets, not only hot Jupiter, also for warm Jupiter, compact multiplanet systems, and etc. For the second one, it suggests that the spin-orbit misalignment in hot Jupiter systems result from the post-formation, specifically high eccentricity migration. It is very easy to understand. High E is an extreme violent process which can naturally lead to the spin-orbit misalignment. If this is true, this process can only apply to hot Jupiter because warm Jupiter cannot form through high E. Their para-electron too far to be tidally circularized. So, to distinguish these two categories, one of the best ways is to conduct the Rosette-McLaughlin effect, or generally, stellar obliquity measurements for all types of exoplanets, especially warm Jupiter. However, before, there are only a few warm Jupiter get their stellar obliquity measured. Here is a plot for all exoplanets. The x-axis is period, y-axis is planetary mass. Those systems with their stellar obliquity measured has been color-coded. Deep color, large stellar obliquity. As you can see, most of stellar obliquity measured was conducted for hot Jupiters. There are only a few measurements for warm Jupiters. You can see here. That's because detecting warm Jupiter was very difficult before, at least before TASS. There are two primary reasons here. The first one is those ground-based telescope surveys found it is very hard to detect warm Jupiter as their period is relatively long, requiring a longer time baseline compared to hot Jupiters. Here is a histogram for planetary orbital period, y-axis is the number of planets. This data from a series of ground-based telescope surveys, SuperWASP, HARTNET, HARSOS, TRASS, CALT, EXO, and so on. So you can see here, the detecting efficiency significantly decreased beyond several days. That basically means those ground-based telescope surveys hardly detected any warm Jupiter before. But certainly, we have amazing Kepler. But Kepler has its own limitations on detecting warm Jupiter here. Limited field of view, relatively faint targets, and the low occurrence rate of warm Jupiter resulting in a few detection of warm Jupiters around bright stars suitable for the following detailed studies, especially radial velocity observations. But TASS mission changed this situation. It's a game changer. Since the first data release from TASS, the number of the known warm Jupiter just increased, dramatically increased. So, okay, I can put this on a more straightforward way here. Here is the annual discovery rate for warm Jupiter. The x-axis is the year of discovery, y-axis is the number of planets. Before TASS data release, the annual discovery rate was below than 10 warm Jupiter per year. You can see here, it's a 10. But after the TASS data release, the number of known warm Jupiter systems just skyrocket, especially those around bright stars, facilitating a series of detailed radio velocity studies. That's a warm Jupiter opportunity provided by TASS. So taking advantage of that rare opportunity, our group, Professor Menderes and Professor Song Huang initiated the SOAS project to extensively observe the stellar obliquity for warm Jupiter population. This project had been empowered by a series of amazing instruments, primarily NUAID, HERES, and PFS. We really appreciate that, the team's efforts. Thank you so much. In the last few years, we conducted numerous velocity measures for warm Jupiter systems. Here, I would like to highlight the recent work I led, including 6 new measurements for warm Jupiters. You can find here the perfect aligned signal here. All of them are aligned. So that leads to the first takeaway. First takeaway from this talk. Single star warm Jupiter tend to be aligned. You may be wondering about the significant level of this tendency. Here is a plot can give you an intuitive understanding of how significant it is. The y-axis is a projected spin orbit angle. The axis is a semi-major axis normalized. The left part is hot Jupiter, right part is warm Jupiter. So it is very obvious, right? Some hot Jupiters can have high obliquity, but all single star warm Jupiter are aligned. Here, you don't need to do any fancy statistical analysis here. You can just get the conclusion by eyeballing this plot, but we still did a calculation for the significant level, which means the final value is 4.3 sigma. That basically means compared to the stellar obliquity distribution for hot Jupiter systems, warm Jupiters are preferentially aligned. You might be wondering about another question here. Since the difference between the stellar obliquity of the hot and warm Jupiter systems is extremely different, so what about the temperature-lambda relation here? What's the temperature-lambda relation for those single-star warm Jupiter systems? This is the second takeaway from this talk. Single-star warm Jupiter systems tend to be aligned, even around hot stars. Famously, the most notable feature for the stellar obliquity distribution for hot Jupiter systems is here. Cool stars, hot Jupiter around cool stars tend to be aligned. But hot Jupiter around hot stars can have a high stellar obliquity. The lower panel is showing the stellar obliquity distribution for warm Jupiters. You can find here, all of them are aligned. So we have enough warm Jupiter systems beyond the craft break, as mentioned by Gigi, to support that warm Jupiter systems do not show the same temperature lambda relation as hot Jupiter systems. Okay, we also did a significance level calculation here. It results in 3.4 sigma. Here, you may be wondering about the significance level and how many additional warm Jupiters we need to achieve with 5 sigma. After we published this paper, probably about half years ago, just tons of our measurements for hot Jupiter, warm Jupiter just came out, pushed this value to a 4.1 sigma. And I did a simple calculation before I write here. We need additional 5 aligned single hot star warm Jupiter to achieve a 5 sigma. So we probably can achieve this goal this year, even this semester, but definitely depending on the weather, even the weather on Cape Peak. So okay, let's back to the question we want to answer through SOAS project. Is the misalignment primordial, or does it result from the post-formation, specifically high migration? Through SOAS, we now have the observational evidence from warm Jupiter, the alignment tendency for single-star warm Jupiter systems. This indicates that spin-orbit misalignment currently can only apply to hot Jupiter systems, and we don't see that relation in warm Jupiter systems. Okay, I can stop here, and I would like to take any questions.
Lots of time for questions. In the middle row.
Hi, I see that you sort of defined the hot versus warm Jupiter boundary as 11 A by R star, but could you expand on that boundary a little bit? And like, what exactly is the border between hot and warm Jupiters, and does that relate to tides? You know, what motivates that difference?
Yeah, I assume you are talking about this one, right?
Yeah.
The boundary for normalized semi-major axis equals 11. So that's a boundary that tidal can work. So that's a very simple question here, an answer to your question. So this boundary basically can control whether that tidal can happen or not. So here, we use that boundary as a criteria to distinguish warm and hot Jupiter.
And does that boundary vary by stellar mass or anything like that?
Basically, the distance separation between the star and the planet, and also the planetary radius.
Okay.
No further questions? David?
So, is there any difference in the density of the planets between the warm and the hot Jupiters? Not just the mass and the radius, but the actual density.
Yes, that's a good question. Off the top of my head, there is no much difference between warm and hot Jupiter for this work. But if we want to ask, I would like to mention the sub-Saturn. I also observed a trend for sub-Saturn. That's pretty new, but I would like to share here. Can I use, wait a minute. There's, okay, wait a minute. We didn't see any specific or certain difference on the density, but we see this trend for sub-Saturn. More puffy, more misalignment. But currently, we don't have a very specific explanation for this, but I would like to open this question to our people here, and definitely would like to talk more about this tendency. This is pretty new, but thank you for asking.
Okay, excellent, thanks.
All right, maybe we're ready to retire for the day and to go for dinner. So let's thank Jian Yu and all the speakers of the day.